Thank you. And it's my honor to have this talk about the gallium oxide, the wide bandgap material, and grown on the SapphireSubstrates. And I will discuss about the electrical properties and some related device performance. So, okay. Oh. Yeah. Then, oh. Okay. And I will first give you an overview about the gallium oxide materials properties and why it is very important and has high potential in the semiconductor industry. As compared with the previous talk, the more mature the gallium nitride or silicon carbide material, and what will be the advantage and also the application. Then I will discuss about the deposition method. Here I will focus on the MOCVD, and also the in situ doping, because if you want to have a good device performance, then typically we should have the N-type dopant and the P-type dopant. Right now, the P-type dopant also achieved and very stable and confirmed by many other cooperative groups. And here I will first talk about the MOSFET, about using the gallium oxide, and then the in situ doped, silicon doped, using the tail source by the MOCVD. And if I have time, I will discuss about the Schottky barrier diode performance. And also, you know, the gallium oxide is a very wide bandgap, so it especially is suitable for the solar blind detector array image sensor. So the deep UV photo detector, not here. And also, because it's wide bandgap material, it has several potential for the pH and also the glucose sensor. So then I think from the silicon germanium, gallium oxide, indium phosphide, my PhD and the master thesis focused on the indium phosphide. Then the gallium nitride, silicon carbide, right? Maybe in the near future, I think the gallium oxide will be a new area of semiconductor. And one important thing is for the box substrate, the melting point for different semiconductor have different melting point. The gallium nitride over 20,000, over 2000, and also the silicon carbide, the 2070, 30. But for the gallium oxide, only 1,700. So its melting point is lower than the gallium nitride and the silicon carbide, and only a little higher than the silicon, conventional silicon. So for the bandgap point of view, the gallium oxide between the diamond or the aluminum nitride and the silicon carbide, this is its bandgap, and also the bandgap corresponding the breakdown coefficient field also better than the silicon carbide or the gallium nitride. Then the gallium oxide has various kinds of what we call a crystal polymorph. That is the alpha phase, and also the beta phase, and gamma, delta, epsilon. And the most stable phase is the beta gallium oxide. Why the bandgap a wider range? That means it's different crystal phase will yield different bandgap energy. but typically the high visible in transmittance in visible region, and also the transparent conductive oxide is also can be achievable. This is the different phase about the gallium oxide, and the most stable is the beta phase. When we have the low temperature epsilon phase, we can typically in the MOCVD reactor we can achieve the epsilon phase. Then if we raise the gross temperature, it will become the beta phase. And also if you grow the gallium oxide by the solution you will have some precursor, the GaOOH. Then after heating to high temperature, it will become the beta phase. So the beta phase is the most stable under the growth condition. And so one of the advantage about the beta phase gallium oxide we expect is high breakdown field, higher than the gallium oxide or gallium nitride or the silicon carbide, and also the thermal stability. So this is the unit cell for the beta phase, the gallium oxide. The red ball is the oxygen. The green ball is the gallium. You can find it's a monocyclic crystal structure. It has different axials. So this also very favorable to the crystal growth by not only by the Czechoslovsky growth method. From the crystal point of view, you can using the melting flow zone. And so here you can clearly see the gallium oxide, the breakdown field, and also the electron mobility. And one special is the Bandgap FOM. As compared to the silicon, the Bandgap FOM is over 3,000. So it is from the silicon carbide and gallium oxide as compared with these two more mature material. Gallium oxide has high potential for high power, high frequency equipment, and also for the high Bandgap FOM as compared with the silicon for the high power component is with high potential. So this is different phase about the alpha, beta, epsilon. Different phase have different band gap. So you can find the Bandgap figures of the FOM using this formula. We can find this is the silicon IGBT, silicon carbide, and this is the gallium oxide. But right now, how to achieve? Because this is the 2 to 6 inch, the gallium oxide substrate. This is 2 to 3 inch, 2 to 6, 3 inch. A very high expensive. And if we can grow the gallium oxide AP layer on sapphire substrate, the sapphire substrate is very mature and with cost-effective price. So this is what my talk focus on the gallium oxide AP layer grown on the sapphire substrate, not on the homoepitaxial growth gallium oxide substrate. Because the beta phase gallium oxide will with close lattice match with the C-plane sapphire. So this is the, for example, this is the sapphire, this is the gallium oxide. So there exists only 6% mismatch between sapphire and the gallium oxide. So the importance in semiconductor industry, that means the high power, high voltage application potential, and maybe alternative to the silicon carbide and the high efficiency, and also increase the investment in research and development. And right now, the 4-inch and 6-inch, the native wafers are available in the market, despite the price. So there are a lot of application field. We have tested not only the Schottky diode, the MOSFET, also the deep UV detector array, and also the pH and the glucose sensor. So this section we talk about the material deposition. This is we using the MOCVD material, the MOCVD reactor, and grow by the gallium oxide, and from the 2-inch and to 4-inch. And the most important parameter is the temperature, because temperature will determine the crystal phase, especially not a little different from the nitride material, because the oxygen to the gallium ratio are also very important. So here, for this slide, show the beta phase can be achieved about in the from here. This is the from 800 degrees C to 900 degrees C. You have different degree. You have this. This is the thickness, and this is the thickness, and this is the growth rate. And also, this is the surface morphology. Also depend on the growth temperature. And this is the gallium flow, effect of gallium flow on the surface morphology. And when the TEGA flow rate increased, the surface roughness will increase. So, and also the different growth time, the time evolution, about this 5 minutes, this 10 minutes, and the 13 minutes. And after the 30 minutes, the completely merge together. And also, this is the different growth parameters. So, in all, I think the growth will be, the initial growth is the Balmer-Weber growth method. Then, and the transition, and then to this SK growth mode. So because it has the dislocation, because it still has the exist 6% lattice mismatch. So we have to overcome the interface engineering and to something like the gallium nitride on silicon. It can be overcome by the interface engineering and to achieve the smooth gallium oxide epilayer. So right now I will give some example about the device. The first device is the MOSFET with various UID. UID, that means intentionally doped. So this is the totally fabrication process for the MOSFET. Then here we have different kind of UID. The UID, and the effect of the UID, it will control the I-on and I-off ratio approximately 10 to 5. And also the positive VTH indicates the E mode due to the thin N there. So this is the UID thickness affects the turn on current. And also this is the UID for the field plate, the breakdown voltage. The breakdown voltage about the 910 volt with the source field plate using this MOSFET structure. So the impact of the voltage enhancement with the source field plate and the effects of the UID, we can find the UID thickness on the MOSFET characteristic. And if we control the UID thickness, we can modulate the MOSFET electrical performance. And also, it will enhance the breakdown voltage performance. Okay, then we can continuously retune the MOSFET performance with different etching depths. The different etching depths, something like this is the MOSFET, and we can etch the UID thickness, and this is the crystal quality of the UID. And if the UID thickness increase, also we can have better crystallinity. And this is the UID, different UID with the MOSFET, the IV curve. So the most important is the impact of various etching depths of the beta phase gallium arsenide MOSFET performance. It can switch from depletion mode to enhanced mode using the mode switching with the gate recessing. And also the significant influence on threshold voltage, also the maximum current and the breakdown. And also the breakdown voltage can be increased to 770 volt with a maximum current of the 140 microamp per millimeter. So this is also can couple with the N-type doping. The N-type doping, if we can have the N-type doping, then we can further increase the MOSFET and also the channel region. So, and because I have not much time, so I think I can briefly show the in situ silicon dope. Because there are a lot of dopant can achieve N-type gallium arsenide. But here, we can consider the tin and also the arsenic and also the gallium and also the silicon. And this different kind of dopant, which is better? The first principle simulation can give some trend. So we can find this is the first principle simulation of the dope gallium arsenide, and finally we find the silicon. The silicon, if the silicon replace the gallium side, will contribute the electron, the gallium arsenide. The band gap is about 2.3 electron volt. And also we can, from this continuously, this is the conduction band, valence band, and Fermi level. And if the gallium replaced by the silicon can make the replacement can about and forming the N-type here. So from the simulation, we can have a lot of calculation, and finally the activation level, the gallium oxide with the silicon, can the lowest level 0.45 electron volt can be achieved. So it is more easily to make activation. So then we using the tail source in the MOCD, and this is different concentration, and different concentration also will achieve different crystallinity and also the surface morphology. So then we will jump maybe, this is for the SIMS, using the SIMS to characterize the in situ dope and the silicon dope concentration. And finally, I think we can have this is the static barrier diode structure for the 5 micron the LS length with or without UID on the sapphire substrate. We can directly find this is the sapphire and this is the buffer layer, and using the tail doped silicon doped N+ gallium oxide. Then this is for the OMI contact, and this is also if we can add an UID material, then the static barrier diode performance will become better. And finally, we can find this is for the IV curve, and on-off ratio can achieve about the 10 to 7, especially with the UID. So, and this is the breakdown field that become 5 order with or without the UID, and the maximum breakdown voltage can achieve the 760 volt. So for the electrical properties of the silicon doped gallium oxide, I can summarize the N-type gallium oxide can be simulated by the silicon, replace the gallium, and represent the loss energy by the first principle. So the simulation and expected performance is correlate very well, and we also using the tails of a very conventional source as the MOCVD precursor, and also the resistivity and concentration can be controlled by the tails flow rate, and we also find the resistivity can be reduced, and also the corresponding concentration can increase. So the N-type behavior can contribute and make better device performance. So, okay, I think the other is the acknowledgement. So that's my talk. Thank you very much.
Right, the talk open for questions.
Since Professor Wu, for the last talk, I have one question that I come from the Honghai Research Institute, and I have one question that how about the reliability performance? Is there any result for the beta gallium oxide? Thank you.
I have no reliability test yet, but as far as I know, the device can be operate at very high temperature. Yeah.
Any more questions? Maybe let me ask one question. I'm interested in the the current you can supply or can be used for this application, because at this time I think current level is quite low. So what will be the main challenge for you to make this activity can operate in a very normal current density for that?
Yes, that's everything from the material quality, because this is the heteroarchitectural growth. So there exists only the 6% lattice mismatch. Although the gallium nitride can have perfect crystallinity after the interface engineering, but for the oxide semiconductor, the architectural growth mechanism is not very clear, because it's totally different from the 3-5 material. For example, not only the temperature, but also the gallium to the oxygen ratio. And also, you can growth rate very low But in some device case, we should have very high deposition rate. So the high growth rate condition and the low growth rate condition is also totally different. And another point is, for the MOCVD, everyone knows if you have the shell head structure, and if you have the high-speed rotation structure, the condition also totally different. So which will be the optimum growth condition for if we want to achieve the very high quality epitaxial layer, the hetero epitaxial layer. So if you can have the native substrate, that's good. The native substrate, the interface can be easily achieved, easily solved. So I think more and more material scientists should contribute to how to overcome the material quality for the hetero epitaxial growth. That's my point of view. And if we can make more perfect material, then we can increase the current density.
Yeah, but as you said before, the bulk gallium oxide growth is almost a similar kind of condition compared to the sapphire, right? So there's no reason it will be so expensive. So if one day the bulk substrate become cost effective. So you think all this epi growth on the bulk gallium oxide will resolve the issue here?
My previous talk about the crucible, for the gallium oxide, the special crucible is a key issue. So it's totally different from the sapphire growth. Even the heat, the reactor, but the crucible material is a key issue. Yeah.
Okay, any more questions?
May I know what's the temperature range for your bulk material growth?
The melting point is the 1,400. Yeah. Yeah.